So now for something totally different. What's different about this? Well, it'll be painfully obvious what's different about it. But this seems just like completely random, totally doesn't make sense to what we've done so far. But this will connect us into what the major chunk of the second half of the year is about. The first half of the year is all about derivatives mostly. This connects us into what the second half of the year is about, which is, anybody know? Antiderivatives. There we go. Okay, so I already talked about that. All right. What we're going to be doing is finding what's called, what is the area under the curve. Now, what we're going to do primarily is spend some time figuring out how you do that, and then we'll go back in and layer on the meaning behind that and why we're doing that. So first, figure out the how, and then figure out the why. In theory, the why drives why you do something, but you got to know how to do it before you can get anywhere with that. So I'm going to start with a super easy one. Don't write this one down. Just kind of look at it. I want to find the area under the curve, and the curve, air quotes in this case, is y equals x. So not a curve, just a straight line. But from 0 to 3. Now when I say area under the curve, what I mean is below the curve but above the x-axis. So the bounded area in there. Super easy geometry question. Area under the curve, well, it's a triangle, so 1/2 base times height, right? Add them up. 3 times 3 times a half, 9 halves. Yay. Easy as that. But, you say, what if it's not a straight geometric kind of a shape? And so how do I find the area under an actual curve? So let's start with an easy one. So the example I'm going to use here, I'm always using x squared on this one. What I need to do then is try to create some geometric shapes out of this. So I'm going to chop up this area into little rectangles. And I can do that a whole bunch of different ways. But the process we're going to use is to create subdivisions. So I'm doing 3 units wide, right? This thing is 3 units wide. And I'm going to go from 0 to 3, find the area. I'm going to choose to create 3 subdivisions. 0 to 1, 1 to 2, 2 to 3. 3 subdivisions. And what I've done with the rectangle is made the height of the rectangle the function value on the left-hand side. So from 0 to 1, the function value on the left-hand side is 0. From 1 to 2, the function value is, on the left-hand side, the value at 1, which, remember, this was x squared, so the function value is 1. And then the function value at 2, again, x squared, it's 4. And so the height of this, although you can't see it, rectangle right there is 0. The height of this one is 1, the height of this one is 4. And each of them have a width of 1. Now it's not a very good estimate, but it's an estimate. And that's kind of all we care about. I'm going to move this thing because there's a big old glare right in the middle of the screen because of the, there. No, now at least the glare is off to the side now. Not a very good estimate, but an estimate nonetheless. By the way, an overestimation of the actual area or an underestimation of the actual area? Because every single one of the rectangles is below the curve. So there's a whole bunch of area I'm not accounting for. But if we did this problem, we would all get the same wrong answer if we set it up the same way. So to make it a better estimate, take the width of each of these intervals and make it smaller. So instead of going 0 to 1, 1 to 2, 2 to 3, go 0 to a half, half to 1, 1 to 1.5, to 2, 2.5, then to 3. And so let's figure out what this would become. Still, do you notice it's a left-hand approximation? Because every rectangle, you pick any rectangle, and the height of the rectangle is the function value on the left-hand side. So I'm doing what's called a left-hand approximation. So let's take a look at some of the numbers. Now, do you recognize that every one of these intervals is half of a unit wide? So the first rectangle is going to be 1/2 times whatever the function value is there. Well, on the left-hand side, I'm putting in 0, so I get x squared is 0. And so on and so on. And in every single case, every one of these has that constant width of 1/2. So being the algebra students that you are, factor out the 1/2 and put it out front. And then these are the function values at every one of those points. So notice, I'm going to go by halves. 0, this is at 1/2, 2/2, 3/2, 4/2, 5/2. Notice there's no function value at 3. Because in that last interval, go back a couple here, in this last interval, the height of this rectangle is the function value at 2.5. So I don't use 3 in this calculation. Even though I'm going 0 to 3, I don't use 3. I used 0, that's the left-hand side, then 1/2, 1.5, 2, 2.5, done. There's 6 intervals there, right? 0, 1/2, 1.5, 2, 2.5, I lost track. Where did I miss one? 0, 1/2, 1, 1.5, 2, 2.5. There it is. Go back, listen to the video, see what I missed. I missed one somewhere. All right, so back to where I was. So, do the math, right? Add them all up, you get that. What was the answer I had before? I didn't get an answer before. Yes, I did. Didn't I get? No, I didn't get one. Let me go back and get one back here. Let's get one from this. So this would be, each of these is 1 unit wide, right? Function value on the left is 0 plus function value at 1 is 1 plus function value at 2 is 4, and I don't use 3 because that's on the right hand side, and so add them up and I get just 5. So what was the estimate I had here then? What is that decimal? 60, 56, not quite 7, right? All right.
7.94.
So,
Oh, sorry, 6.94.
so, if I wanted to get an even better estimate, instead of making the width, now, recognize the notation, right? Delta x means the difference in the x values. So instead of making the width of each one of these rectangles 1/2, I could make the width of each rectangle 1/4. Now, don't write this down, but it just gets really messy when you start doing that many. But how many subdivisions would there be? On 3 units wide, I'd have a total of 12. So what this equation gets you
So you ran the program?
is the number of subdivisions within that interval. So b minus a, so in this case I went 3 minus 0. Each one of them is going to be 1/4 of a unit wide. So 3 divided by 1/4 is 12. Right? Division by fraction, same thing as multiplying by the reciprocal. You can rearrange this in any way, depending upon what you know and what you want to find out. So if you knew I've got b minus a, that's how wide the interval is. And if I knew I wanted to have 10 subdivisions, I could divide by 10, and that would tell me how wide to make each one of them. So you can rearrange that, solve it for whichever variable, whichever piece you want to know. So if I did that, does it make sense that the more intervals I've got, the closer I'm going to get to the actual answer?
Yes.
Now in this problem, every single one of those was an underestimation. Because always when I'm on the left-hand side, right, I'm going to be picking the smaller value. Let me put a little aside in here. What happens if I have a function that looks like this? And I do a left-hand approximation. Now, you're going to be getting an overestimation on that. So what's the determining factor about whether it's an overestimation versus an underestimation?
Whether or not it's increasing or decreasing.
Yeah, yes, but an easier way of saying that is just increasing, decreasing. An increasing function, if you choose a left-hand side, if it's an increasing function, when you pick the number on the left, you're always going to be picking the smaller number. If it's a decreasing function and you pick the number on the left, it's always going to be an overestimation because you're always picking the higher number. In a moment, we're going to go to a right-hand approximation, which just turns that around, right? So here's all the numbers. So I had 12 of them, right? Because it was 3 units wide, and I was doing delta x is 1/4, so wacka 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 boom. But it's real simple because it's just x squared. So it was 0, 1/4, 2/4, 3/4, 4/4, 5/4. You could just do it that way in squaring them. Add them all together, boom, about that. A little bit higher than I was a minute ago, right? Hi. Quality test? Yeah. So, here, go sit, I'll get you in a second. So, what you've got here is still a wrong answer, still an under approximation, but a better wrong answer as you work your way up. So think about what we want to do. Which piece do you need, by the way?
Not that good.
So we want to be able to come up with the area under the curve. Just pass it down. Does it make sense? We're going to do a limit, because how many rectangles would I really want to have? An infinite number, as many as possible. But I want to have an infinite number of them. And it takes a really long time to find an infinite number of areas of rectangles. I got a class working on this problem still from last year. They had to move over to Starbucks because the building got torn down.
I'll be back.
They're in the back room. Okay. So, some notation. Let me start building. R in this problem simply represents an approximating rectangle. Notice the vocabulary back here. An approximating rectangle. And what do I want to have happen? It's a limit, but I want the number of approximating rectangles to approach infinity. And what's going on in here is that's just a multiplication problem. F of x times delta x. Delta x is the width of the rectangle, f of x is the height of the rectangle. That's day 2 of geometry. How do you find the area of a rectangle? What makes this a calculus problem is this notation of limit. In the conceptual stuff that we've done with how do you find a limit. And so, a whole bunch of them. Now, a large part of what you're going to see in the next couple of sections has to do with notation. Being able to recognize notation and not freak out when you see it, but be able to use it and go, oh yeah, I know what they're getting at there. This is just simply finding the area underneath a curve. And again, under the curve but above the x-axis. Nothing magical about the left hand. Of course, this is my right hand. Nothing magical about your left-hand approximation. You could choose a midpoint approximation if you wanted to. So on the interval from 0 to 1, the midpoint would be at 1/2. 2 halves, this would be at 3 halves, and 4 halves, and then 5 halves. Now, the nice thing about that is that you've got a little bit of over-approximation stuff here, but then you also got some under-approximation. They kind of ish cancel each other out. What's delta x in this problem? Still 1. The width of the rectangle is 1. What's f of the first value? 1/4. Because you remember it was x squared. So 1/4 plus 9/4 plus 25/4. What do we got? 35/4. Not quite 9, right? 36/4 would be 9. So not quite 9. A little bit higher than the last one, but now I don't know if this is an over approximation or an under approximation, because I don't know if this area is bigger than that area. I don't know. But it might be a better answer. There's a lot of, what you're going to find in calculus this year, a lot, is that good enough is close enough. Every answer we have found so far is wrong, but it's a good enough estimate. Yep, walk away at that down there. 8.75, is that right? Is that what I had? Now, here's the one that's kind of fun. A trapezoid. And the reason the trapezoids are kind of nice is the concept of locally linear. If your interval is small enough, no matter how curvy it is, it's going to kind of be a straight line. And what you get, of course, with this side of the trapezoid is a straight line. And there's not very much missed or unaccounted for or overestimation in this case. By the way, in this particular picture, will this be an overestimation or an underestimation? Because, ooh, I like that. The secant line is what?
It's above the.
Yeah, what happens if this is a decreasing function?
Wait, no, it'd still be an overestimation.
What's going to determine?
It depends how it's decreasing.
Okay, so what's going to determine whether it's an over or an underestimation for trapezoid? A moment ago we decided it was whether it was increasing or decreasing. I can have an increasing function that looks like this, and now when I do a trapezoid, it's going to be an under approximation.
It's concavity?
And what the difference is the concavity. Second derivative, right, tells you concavity. So, the increasing, decreasing is telling you something for when you're doing rectangular approximations, but the concavity is going to tell you whether it's an over or under approximation for the trapezoid. Okay, so area of a rectangle, easy, length times width. Area of a trapezoid, oh, come on, geometry students. Times what?
Times the height.
Now, here's why. Let me remind you of this real fast. If I take this picture, if I take that trapezoid right there, and I double it, and then I flip that one upside down, now what shape do I have? And what's the area of a parallelogram? Base times height. And so, the problem is that the base is this length right there, and that length is B1 plus B2. The height is this vertical distance, the distance between the two bases. And so this is base times height, and why divided by 2? Because I doubled it to create the parallelogram, so I got to go back to just the trapezoid to get that area. Know that equation. That will absolutely be a question on the exam. If not the AP, mine. It comes up every other-ish year or so where you have to do a trapezoidal approximation. Know that. Know that. Okay, so sometimes it's a better approximation because you don't have as much wasted area. Depends on how steep the concavity is or how wide you're doing. I mean, if I extended this out a lot, now you got a lot of space in here. So, as is true with the rectangles, the smaller the intervals, the better your answer. But there's a thing I want you to notice here. Notice something about this base. Which base is that? Of which trapezoid? Yellow or green? So it's base 2 of yellow, but it's also base 1 of the next green one. When they butt up against each other like that, the base of one of them is the base of the second base of the first one is the first base of the second one. The point of that being is, when you find these areas, look at what you get. Base 1, base 2. Well, base 2 and then base 1 of the next one. Base 2 and then base 1 of the next one. There's a lot of repeating to these. And so you can take that to your advantage to make the calculation. Even though it looks cumbersome, you can shorten things up a little bit. Now this one I just did because there was only 3 trapezoids. So I'm actually doing the x squared still. So at 0 and at 1, and at 1 and at 2, and then 2 at 3. Now remember on the the rectangles, we didn't use the farthest left-hand side. We didn't use the value at 3. Now I do. I'm using that value at 3. Because it's the second base of this last trapezoid. Wacka, 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 boom. Overestimation, underestimation? Because it's a concave up shape. And so every single one of the trapezoids gives me something over. Let me think about something here for a second. Yeah, the actual answer, by the way, is 9. So if you take a look back at your work, at the ones we've done, you should see them kind of approaching 9, but those were underestimations. This is 9.5, but that's an overestimation. We'll get to that later on. So I already talked about right-hand approximation. It's as good as an estimation as any other pick, right? We did midpoint, we did left hand, right hand. Now, increasing function, look at the picture. Increasing function, when you're picking the right-hand side, you're always picking the larger value, you're going to get an over approximation. There's an assumption that the function stayed at this value the whole time. It didn't. It worked its way up to that value, but it wasn't that value the whole time. We're assuming that the function was this value the whole time from 1 to 2. It wasn't. It worked its way up to that value. So at the last second, it got to that value. But that picture's assuming it stayed there the whole way. So again, left hand versus right hand depends upon the overestimation, underestimation depends upon whether it's an increasing function, wrong direction, or decreasing function. If it's decreasing and I'm choosing right hand, let's see, choosing right hand on a decreasing function, I'm always picking the smaller value, it's going to be an underestimation. If I pick what is this? Left or right? If I pick a left on an increasing function, I'm always picking the smaller value, that's going to be an underestimation. So you kind of have to visualize what's going on here in terms of whether it's an over or an under approximation. Okay? Increasing versus decreasing. With the trapezoid, it had to do with concavity. All right, I'm going to layer on some meaning here in a second.
With the midpoint approximation,
Yep.
Is that an under approximation?
It depends. You don't know. Because when it was crossing and some of the area was below and some of the area is above, I don't know which of those is bigger. And it depends upon a bunch of stuff. How narrow are your intervals? How steep is the curve? Where does it zigzag maybe a little bit? You'll see one here in a minute where I do a left-hand approximation, but it's on a kind of a zigzag. So some of them are above and some of them are below. And now you're kind of like, I don't know. So I wouldn't ask the question on that type of a problem. So if I'm driving in my car and I know how fast I'm going, I should be able to figure out how far I've gone. If you know
The way.
if I know one other piece of information. Say again?
How long you've been doing
How long you did that. If I go 50 miles an hour, how far have I gone? If I went 50 miles an hour for 2 hours, now I can tell you how far I've gone. So what we're going to do is basically just that. This is a distance. We're going to be able to estimate distance traveled if I know the velocity. But I'm also going to need to know the time. So here's some random velocity function. Just kind of made it up. So I pulled out of my driveway, I don't know, just randomly make up a number. I'm going 20 miles an hour. Pulled out of my driveway going 20. A little fast, but you know, there were no kids around. Don't do that, that's bad. Don't text while you drive.
You gotta stop.
I should've.
Intoxicated.
All right. So, and then, you know, now be careful. Understand this is velocity. So I'm going faster, 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 faster. I don't stop going fast. Well, let me say this differently. I don't stop. I'm still having some speed. Maybe my speed is 30 now. I slow down maybe to 28, but I'm still, this is all positive velocity. So don't think just because it's going down at some point that I now have negative velocity. These y values are all positive, so you have all positive velocity. I never turned around or went backwards or did anything funky. What's it mean?
Rate time.
Rate times time is distance. For example, 60 miles an hour for 2 hours. Hours would cancel, and you end up with 120 miles. If I know the rate and the time, I can tell you the distance. So look at what I've got here. The height of that function, the height of the function is my velocity, or rate. Along the x-axis is time. So look at one of those rectangles. The width of this rectangle is the amount of time that I did that velocity. Now there's an assumption. The assumption is I did this velocity the entire time. I didn't. I did less than that velocity and worked my way up to that. By the way, left hand versus right hand.
Right in.
Right hand approximation. Every rectangle, the height of it is the value on the right. This is what I was talking about before, Ellie, about how you can, I'm over, but now I'm under, now I'm over and over. So probably this is an overestimation, but you technically can't know for sure. Maybe that I've just drawn it poorly. So you can't say
So,
definitely. But I know that in this first interval, from 0 to 1, that this is an over approximation. I didn't go that speed the entire time, I just did it at the very last split second. But you assume you did, because that makes the rectangles easy to find. Length times width, length times width, length times width. The length is the function value, right? So what this means for us, well, let me back up here. What this is then, this area is an estimation of the distance I've traveled in the first, whatever my units are, second, hour, whatever T stands for here. That's an estimation of the distance I've traveled. So the area under that function represents the distance you traveled. If you have a velocity function, the area under the curve is distance. To which you say,
Wow.
thank you. Now you know calculus too.
I'm pretty sure he told us we could use that. I just forgot to use it.
What?
That in physics in the first course. Not that it mattered, but.
All right. Okay. If you want to know where this example comes from, this is straight out of the book. I forget what the exact scenario is, but I think it has to do with maybe like a rocket being launched or something. And what they give us is a set of data. In the first 30 seconds of some rocket being shot up into space. And I think if I remember correctly, they gave it to us in miles per hour, but then I don't know why they do that, because then they immediately convert it to feet per second. So anyway, these units are feet per second. And the graph ends up looking something like this. And what the question is estimate the height of the rocket after 30 seconds. I'm not sure if they gave you, I have to double check the picture. I'm not sure if they gave you told you exactly how wide to make each of the interval, but I'm pretty sure that they gave us function values at every 5 seconds. So if they give us function values every 5 seconds, you can divide up delta x and make delta x into 5. So if I want to estimate that, so do you recognize that as a left endpoint, right? To pick any one of the intervals, where does the rectangle hit the graph? And in every case, the rectangle hits the graph on the left-hand side, right? Pick any rectangle. The height of that rectangle is on the left-hand side, so left-hand approximation. Again, you can't tell for sure if it's an over approximation or an under approximation. It looks probably for sure it would be an under, but I wouldn't ask the question in this case. So, do the computation. So they've given us all of these function values at every single one of these points. Notice, 1, 2, 3, 4, 5, 6. So I'm doing 30 seconds. That's the width of the interval. delta x is 5, sure enough, there are 6 subdivisions. Remember that little equation I said no? This is b minus a, so 30 minus 0 over delta x equals the number of subdivisions. Or 30, that's a 3, 30 over 6 equals 5. If you take the width of the interval and divide by the number of subdivisions, you get the width of each subdivision. Just rearranging the equation. And so they give us these function values. They gave us f of 0, f of 5, and so on. And so plug and chug. Now this was 0, 5, 10, 15, 20, 25. How come I didn't use 30?
Because it's left hand.
Because it's left hand. And the 30 is on the right hand side. So when you look at this picture, the height of that last rectangle is based upon the function value at 25, not the function value at 30. That's the thing people screw up all the time. You're thinking, I'm going 0 to 30, I've got to use the 30. Not if you're using a left hand. But, you say, what if I change this to a right hand approximation? Yes, sir?
And you don't use 0.
Now you don't use 0, and you do use the value at 30. So if you're doing this on your calculator, don't retype the whole thing. Just go in and change that first one. This was f of 0. The 25, can't get it, is f of 0. Take the f of 0 out and replace it with what f of 30 is. Because all the other numbers are still the same. Because when I do this and change this to a right approximation, the height of this rectangle is the height that the left-hand approximation was over here. The height of this rectangle on the right-hand side is the height that the left-hand one was just a moment ago. So you have all the same numbers. You don't need to retype them all again. Make sense? Ish? Just swap out. So what did I go from? I went from 1135 to 1215. So probably the answer is somewhere in the middle. But again, close enough is good enough.
Just
All right.
average them real quick or get closer answer.
Say again?
You can just average them and get closer answer.
And that may be even better too. So a variation on a theme. Try this if you're driving home today. Set your trip on the car, you know, the odometer thing where you can say how long you've driven, and measure exactly how far it is home. And then have, assuming you're not just sitting in traffic, although that would work as well, but then have the passenger, don't do this while you're driving, because you need to pay attention to the road. Don't text while you drive. Have somebody every 5 seconds glance at the speedometer and record the speed you're going. That's a lot of effort, all the way home. But do the calculations, see if it comes out to the distance that you are. I mean, even if you're sitting in traffic, if you're going 0 miles an hour for 5 seconds, you've gone 0. So it should still work. And just simply record the calculation. But as you're driving home, and you're, of course, paying attention to the road and somebody else is reading the numbers off, and you're driving along and suddenly a squirrel jumps out, you go, ah! And you forget to write down the number. Or you write it down too late, or you write it down maybe a little bit too early, or you record it not right at the 5 seconds. Point is, there's nothing magical about left hand versus right hand. There's nothing magical about the midpoint. Any point in the interval could work. And so what this is simply saying to you is, from 0 to 1, I could choose any function value I want. Any x value from 0 to 1 will give me as reasonable wrong answer as any other wrong answer. Right? Likewise, pick any function value you want on the next one. Additionally, remember how I said you're doing this every 5 seconds? There's nothing magical about 5 seconds. Maybe the first one you do 7 seconds, then the next one you do 9 seconds, then the next one you do 3 seconds. The only disadvantage of that is, remember how when we factored delta x out front because every one of them had the same width? Now you wouldn't be able to factor the delta x out. You'd have to do every single calculation with length times width. Different length and width. and so on. So in the book, the notation you're going to see for this, when it's some random point, they put a little asterisk on it, just cause. And so now what that equation that we had a minute ago becomes is this. But recognize this as an area of a rectangle. Height times width. Plus height times width. The next rectangle, the next rectangle, the next rectangle. All the way up to the nth rectangle. And what do I do? How many rectangles do I want? I want to go to infinity. That's a lot of rectangles. Takes a long time to add them up. Again, almost never do you have to write this notation, but you need to read it and understand it and not be freaked out by it. Just recognize that is a real simple geometry problem. Area of this rectangle plus the area of this rectangle plus the area of this rectangle, etc., etc. And how many of them do you want? You take a deep breath there. Now this is the real notation I want you to understand. What's this saying to you?
Summation.
Sigma notation, it's a summation. That's an addition problem, right? So what I'm going to do is I'm going to add up every single one of those
From one.
height times width. From the x sub I, so from the first rectangle to the nth rectangle. But wait, you say,
Wait.
how many rectangles do I want?
Infinite.
An infinite number of them.
Yes, you can.
That notation right there
Just spam a bunch of
is the notation we're going to use that represents the exact area under the curve, not an approximation. That's the exact area.
Is there an infinity symbol in the calculator? Or no?
I'm looking at your calendar.
No. So a little vocabulary for you. This is what's known as a Riemann sum. And we're going to use a Riemann sum to estimate that exact value.
Who's Riemann?
Bernard, dead German guy, mathematician.
All this is Bernard County.
So, see what you can figure out here. Draw this picture, estimate the area under the curve, 4 subdivisions, give me an exact answer on paper without your calculator.
Alright. Type in my calculator real quick so I don't have to write.
Put what in? What do you need to put in?
Did this last year, so. That science thing. Yeah, this is literally my whole section.
I'm watching you, warrior. All right, we got an answer yet? Where's your picture? Where's your picture? That's an interesting picture. No. from one to five.
Oh.
Where are your approximating rectangles? Draw the approximating rectangles.
I got it.
Right there.
No.
Silence.
Got an answer?
No.
I'm waiting for everyone else to get their second line. You can write F lines.
Draw your
Yeah,
approximating
I'll
rectangles.
see it, right it.
Oh no, it's from X equals
Uh-oh.
1.
Yeah, there you go. Close. Picture's wrong.
Is my graph wrong?
No, but your picture's wrong. Because this goes from 1 to 5. You've got a rectangle from 0 to 1. There should be a rectangle from 0 to 1. First rectangle shouldn't show up until you get to 1. So for those of you who started at 0 and went to 1, that was bad.
I don't want to hear it.
Are you supposed to start at 2 though?
No, I'm doing left-hand approximation, I think. No, I'm doing right-hand approximation. Yeah, I'm doing right-hand, but the first interval is from 0 to 1. Bad. From 1 to 2. I use the function value at 2, but the rectangle starts at 1.
Yes.
So Jackson, what's next? What's next? What do I do?
You take the values of each of the right endpoints.
Okay, so I'm going to use f of, uh-huh, and what's delta x in this case? Conveniently, it's just a 1. And because it's 1 for each of them, I can just factor it out. Notice that there are, even though I'm going to 5, there's only 4 subdivisions. So the height of each one of them is based on the right-hand side. 1/2, 1/3, 1/4, 1/5, and by golly, when you add them up, 77/60ths.
Okay then, J House.
Let's go.
But I will ask you to draw a picture to represent what you're doing. I want you to be able to visualize this as well as get this number. Now, do trapezoids. By the way, what was your last answer? Over or under approximation?
Under.
Right-hand approximation for a decreasing function, you're always using the smaller answer, is going to be an underestimation. What tells you whether this one's over or under? And it's concave up, so your approximation is going to be an overestimation. And look at the picture. You've got these little spaces in here that are above the curve. Got this one in your head?
I'll write this down.
Come on, J House.
If you're feeling stuck, this is your generic setup. There's 4 trapezoids, starting at 1, going to 5. But what do you notice here? See? Huh, that guy repeats. That guy repeats. That one repeats. And also notice that there's a 1/2 in every one of them, so I can factor that out. So when it comes to finding these, look what I'm doing down here. Look what's going on down here. This first function value happens only one time. So I'm going to put 8. By the way, what's h in this problem? 1, because the height of the trapezoid is this distance. That's the height of the trapezoid horizontally. And so the height is 1. The 1/2 goes out front. This value only happens one time. But every one of these happens twice. And then this one only happens one time. So look at how I've set it up. It gets a little sloppy down here at the end, sorry. But this is f of x sub 5. And it only happens one side. So I've closed off this doubling out here. I double those middle ones. So I only have to type them in once. Now, so listen. Stop for a second and listen. Because I just learned this somewhat recently on the newer calculators, because most of the ones I have are older. On the newer calculator, remember how we used to go in and get y? We had to go into y variables and go to function and go to y sub 1, and you could pull that out. And so you're able to, like if I wanted to know f of 3 in the calculator, you would go like this. You pull up y sub 1, and you put a parenthesis, and you put it in 3, and now you have to have some function into y, right? Whatever function is in y, it'll evaluate it at 3. So go to your home screen. Put it in x squared just for giggles and kicks. No, what is this function? This is 1 over x. Sorry, put 1 over x into y equals. Put 1 over x into y equals. And then go back to the home screen. Now on the home screen, if you go alpha trace, above the trace is F4, the green F4. If you go alpha F4, it'll pull up a menu for you so you can quickly access the y variables. Yes?
Yes.
And so you select y sub 1, and then go parenthesis and put in whatever number you want. Hit enter, it'll evaluate it. So when you do that with this, you can just type it in exactly. Now you have to put in numbers here, right? So x sub 1 is 1, x sub 2 is 2, and so on and so on. But it'll save you a lot of work to actually calculate that. Hey, why are you making faces? Yours is old, sorry. You gotta do it by hand. So you're gonna have to go. So if you were trying to do that, you'd go 0.5 parentheses, then you gotta go variables, y variables, function, y variables, parentheses, put in
He
1.
was not talking, you were talking.
Plus 2 times.
Wait, why would you?
If you ever
Because
need
that's
watch
the
somebody, I got
first
you.
base is at 1. Right here, we're going from 1 to 5. So the first base, this is trapezoid, f of base 1 plus base 2. Base 1 happens at 1. Look at the picture.
Don't phase over.
Base 1 happens at, these aren't numbers. Base 1 happens at 1. This is 1 right here. So you got to find f of 1. You're evaluating finding the first base. Yeah.
So that equation in red that you like simplified it to,
Uh-huh.
can we use that for any of them, or how does
Yeah.
it change?
You change. So if you left that somewhere, or I don't know, yes. Other than if there were more things in the middle, you're going to have to go in. You're going to have to go in and change these to, what if I'm going from 7 to 10? So now you got to put in 7 and 8 and so on. All right. That answer comes out to be that. There we are at the end.
It is gigas.
There are 5 whole problems in this section. Do them tonight. It's been a pleasure. Let's do it again soon.